Hey everyone, and welcome to the energy efficiency gains from or for electrified hydraulics. My name is Marcus Herrera with HYDAC, and I helped co-write a white paper for the NFPA on how we might get energy efficiency gains when using electrified equipment in hydraulic machines. So, what's the background of this white paper? Why did we write it? Well, if you guys have been around NFPA for any duration, you've probably seen our technology roadmaps. These roadmaps helped outline and trace some trends that we're seeing in the industry. And we're specifically looking at the 2023 technology roadmap, where we identified some key players that include energy efficiency gains within hydraulics. So this paper is writing about what that is. And just to state also, when we talk about energy efficiency gains, we're speaking on how electrified products or electrified components within a hydraulic circuit might introduce some energy efficiency gains. There is an architecture where we could go full electric, where we have no hydraulics in the machine at all. That does not necessarily fit what this paper is about. This paper is really about when we're using hydraulics in electric equipment, how can we increase, what are some areas we can look at to increase the efficiency, and why is it important? So, to sum up the introduction here, I want to state that this paper is not to pursue or convince you guys, the listeners, to go for electrification. If you have already chosen electrification as part of your journey or you're interested in that market and want to learn more about it, the goal of this paper is really just to outline the current states of that market and where there are some key benefits when using electrified equipment. So let's kick it off. What are the needs and the drivers for this? Well, mostly they're governmental stuff. We've had some federal and state tax credits that have been released. There have been some regulation zones, primarily in Europe, that are saying, hey, for health and safety or for limiting noise, we'd like to introduce some more electric equipment. But also, it's been an interesting look from the market itself, wanting to try to find where we can eke out that extra bit of efficiency when it comes to our machines. So that leads us to addressing the inefficiencies of internal combustion engines. Instead of reading the text, we're going to look at this picture down here at the bottom. And really, this graph shows the difference between a conventional power source and electrified power source. That could be a battery, that could be a fuel cell, basically anything that isn't conventionally like an ICE engines, like a diesel. So on the left here, you see this diesel tank that's considered 100% full. That means 100% of the energy found within that diesel is available. As soon as I key on that machine and I run through that diesel fuel, 65% of that available energy within that fluid is burned off, either in friction, whether that's through heat, exhaust, that sort of thing. So my machine is now left with 35% of the original energy. Once you factor in the inefficiencies of hydraulics, at the end of the day, let's say from the diesel tank to the bucket tip, I'm left with 18% of energy that's used in the actual function of that machine. When we look at an electrical power source, things are a little different, primarily because of the inherent efficiency of our electric components. So when you look at the average inefficiency of a motor or inverter, you're talking like 85 to 90%. So in this chart, we assumed 90%. That means that if I take my fuel cell or my battery at 100% capacity and I run it down to zero, I'm actually left with 46% of that available energy ready to do work. And I think this does a pretty good job explaining where the key is to look for and why the market's kind of trending in that direction of electrical power source is a pretty efficient use of the energy once it's already on board the machine. So to the next step, we're going to talk about how motor sizing and motor selection is a little bit different for electric motors versus conventional internal combustion engines. The only reason I bring this up is because a traditional way that you would size a machine is through a thing called corner power. Corner power assumes maximum flow, maximum pressure, that's where my engine needs to be able to run. Well, when we talk about electrical equipment, they actually are designed and I would say categorized slightly differently. So the duty cycle of our electric motor is categorized within duty cycle, which is to say an S1 or an S2. S1 means continuous duty, S2 means short term or short time duty. And really, it's all a factor of temperature. So my motor might spend most of its time spinning at 3,000 RPM and doing, I don't know, 40 kilowatts of power. But there could be short durations where that needs to spin faster or output more. And that's totally within the motor's capable performance. So the way that you make sure you size your motor correctly is through thermal considerations. We've had some initial inquiries just internally within HYDAC of customers wanting to try their first hand at putting an electric motor on their vehicle. And most of the time, we have to walk them through this concept of these motors do intelligently derate based on the temperature that they're running at. And they fit somewhere in between that S1 and S2 operating range. I think S9 is a pretty interesting view of what that looks like. It's overload capacity for subsequent continuous operation, depending on the preceding operation. That's a long-winded way of saying, depending on how cool my motor has been, I can do some higher capable things that add some heat soak into it, as long as I wait long enough for my duration and let that temperature go back down. So just an interesting thing to look at when you're talking about introducing electric motors and for the first time. There are some unique features that make it different from a conventional internal combustion engine. So when we look at that original chart that we had before, we talk about 100% energy, 18% being usable versus 46 being usable. Let's say we wanted to increase the hydraulic efficiencies within this, right? Let's say by 20%. What does that look like? Well, on the conventional power source, you gain 6% energy usage, but on the electrical, you gain 15%. And this really highlights the importance of using energy efficient hydraulics when you have any sort of electrical architecture on your machine. That electrical architecture is expensive. It's hard to get that energy on the machine, but the machine uses that energy more efficiently. And so we really want to capitalize this increase of energy efficiency. Now, where might we focus when we're trying to increase hydraulic efficiency? This really cool chart from the OEM off-highway sums it up quite well. They look at a mini excavator, and in general, they estimate over 50%, 32 and 19% respectively, of all hydraulic losses are found within metering in and metering out circuits. So what does that mean? What does that look like? Well, a metering out circuit is any time I want to restrict the flow leaving my actuator. So that could be in multiple different sources. I'd say a primary one might be a load holding valve. So anytime I have my front function lifting anything off the ground, that machine for whatever reason needs to turn off, or if we need to stop that load, we don't want that load to droop. We want that load to be held in space. That's primarily a safety risk, but it's also reducing just our internal leakages and hose ruptures or pump failures, right? So anytime we have any suspended load, we might have a load holding valve. So that's one area. And the reason why this causes inefficiencies is if I have a 50-ton excavator, but my bucket is completely empty, that load holding valve needs to be rated for holding 50 tons in the air. But my bucket's empty, so my pump actually has to power through that spring to push the bucket down. It can't use gravity to help. Well, I mean, it does, but it doesn't overcome the spring. So that's an inefficiency where if we can get smarter with instead of using a simple spring and we start using pilot operated load holding valves or even electrohydraulic load holding valves, we can greatly increase the efficiency of our metering out. When we talk about metering in losses, what we're doing is restricting the flow going into the cylinder. So that could primarily be seen when we're trying to do precise speed control or small movements. If we're trying to gently raise the boom, if we're trying to adjust it very small, such as a telehandler, we might care about making very small adjustments and we don't want a whole bunch of flow going in. But maybe our pump can't spin that slowly, or maybe our engine typically can't spin that slowly. So we have some way of restricting that flow going in. A very ideal but impractical solution is every single actuator within my machine has its own pump. And that pump is specifically sized for the speed and the force that needs to go into that. But a large majority of the time, that is not the case. We have one major source of fluid power, and we have to distribute that fluid power within the machine. So we use things like metering in valves to help guide that fluid to where it needs to go and also give it some speed control and force control. Ways that we can improve metering in losses could be, again, similarly, pilot operated valves where we're not directing all of the flow, we're only directing a small portion of that flow to move the valve, or proportional control valves. So instead of using on-off control, we're able to electronically control these valves to be more precise for the specific operating condition. When we look at what is the next stage of electrified hydraulics and electrical efficiency within hydraulics, really it's further advanced look at software controls and sensing. We've seen these in the market for decades now. These aren't anything new, but more and more machines are starting to adopt electrification. They're starting to adopt these controls and ruggedized sensors and software that allow their machine to work even more efficiently than a human could do it. Um, there are some other dynamic efficiencies that we can look into as the software continues to advance. We could do some pretty cool things just beyond operator comfort or controls. A couple examples could be dynamic load matching, where we're constantly adjusting that pump to the actual load. Electric flow sharing, which is a newer but still quite popular thing, where instead of mechanically adjusting where that flow needs to go, we're doing it all electronically. And again, that's a direct correlation to metering in losses. We're eliminating all those metering in losses by knowing when I move a joystick and commanding flow only when I command it, where I command it. And finally, closed loop control, where we're monitoring and adjusting parameters in real time to try to prevent some overshoots and increase our efficiencies with things like PID control. So when we look at our software solutions, really this section of the paper starts talking about what the future could look like. When we talk about predictive and adaptive control, I would definitely say that this isn't completely brand new to the market. We've seen at trade shows some key machines trying this stuff out, but it's not a massively adopted capability within the machine architecture of today. So, what are some of those software controls you might see that help at your energy efficiency? Predictive algorithms, where we can actually look at duty cycles and operator behavior. You take that one step further, you might even have you tag an operator so when he gets in the seat, the machine knows how this operator is performing. Position feedback and command matching. This is similar to if my cylinder is all the way deadheaded and I keep commanding more flow to that cylinder, well, I have a sensor in there that says you don't need any more flow. We're not going to give you that. We're not going to waste the energy to do it. And then there's also user assist functions where an operator that's doing repetitive work or complex work, anytime he has assistance from his software, he can be more efficient with his movements. He has less overshoot, and it also increases the skill of the operator to perform like someone who's been in the field for a very long time. A unique advantage to software-enabled solutions is that there can be continuous improvement with the same software or the same hardware. I'm sorry. So as long as I have my sensors and as long as I have a controller capable enough to do these complex things, all I need to do is send some new software going to that controller to enable any of these features at any time, whether that be behind a locked package of payment or whether that be behind a timeline of development. Now, another future direction we could see is going from monitoring to maintenance. We see a lot of companies out there today doing this. This screenshot is from Elevate as a case study where they're looking at the field units and they're deciding based on what they're seeing through sensor fusion, when's the right time to change the oil, when's the right time to change the filter, um, and maybe do some general maintenance on their machine. But really, I think a key future direction is utilizing autonomy and machine learning on your machines. So many machines that have telematics units have geofencing today, and this section of the paper kind of dives into what else could we do with that sort of data that we're collecting on our machines. So if a machine moves from one area of the job site to another, and I know within that job site one area is leveling and one area is digging, and I have the same machine doing both functions, maybe I can automatically tune that machine to be faster at turning or lifting in one area or another to really optimize the machine performance for the operation that it's doing. This is another area where I reference being able to know the operator that hops in the vehicle at what time during the day during his shift. I can automatically tune that machine to behave the way that the operator likes for it to behave. So we're just another way that we could advancedly increase the efficiency of the operator, which then increases the efficiency of the machine and the energy usage when that machine does work. To sum the paper up with the energy efficiency gains, we've really explored the inefficiencies of the hydraulic architecture in of itself and how we want to optimize and utilize all of the energy on the machine that's in the form of an electric power source, whether that be a battery, whether that be a fuel cell. We know these things are pretty expensive right now, and we know that it's a big undertaking for a supplier or a manufacturer to add these into their machine. So any way we can increase the energy efficiency and performance of those items, the better off both the end customer and the manufacturer will be. Then we started talking about a transition from electrification, and we talked about really the integration into the ecosystem of the machine, where together we're not only providing a monitoring and prediction stuff, we're also optimizing what it means to look energy efficient and how your machine performance can improve. Looking forward at advanced controls and software driven items, we're really just talking about what could be the future. And we feel like all these technologies exist today, and it's just going to be a matter of time before people start utilizing these to the next degree. So we thank you for your time of listening to me or reading this document. We hope it jogs some cool ideas within you and within your industry, within your company. And we hope that you continue to utilize the resources that NFPA has to offer. Thank you.